Hello students, so right now I'll be going through this topic, alkenes, alkynes and enines. So on your slides, if you want to follow me, the first thing you see here on this page is an alkene, or in the olden days they call it olefin. In America they like to call it olefin instead of alkene. So it represents hydrocarbons that contain a carbon-carbon double bond, and we denote it by having double lines, something like an equal line, right, in the line structure diagrams. And this is present in many organic and biological molecules. In us, of course, in plants as well. You have your beta-carotene, which is a pigment and a vitamin A precursor. And this is a structure. You see that there's many alternating double bonds here. Double, single, double, single, double, single, double, single, and all the way. Alright? For the alkyne, it is a hydrocarbon that contains a carbon-carbon triple bond. And you recognize it by this kind of structure, 3 lines. Okay, so this is a triple bond, carbon, carbon, carbon. Between these two carbons you have a triple bond, and then single bond, triple bond, single bond, triple bond, alternating pi bonds. Now this is not very common in biological molecules and pathway because it's not very stable, it's rather reactive. When something is of a high energy, it's not so stable, it's reactive, so it won't stay there for a long period of time. This is an example of S-benzquatinoic acid, an antiviral, anti-HIV agent which is isolated from this species of plant that's found in Indonesia, Malaysia and Singapore. For alkanes, we learned last time that the general formula CnH2n plus 2 is all single bond, saturated, and they are hydrocarbon. For alkene, because now we have got 1 degree of unsaturation, a pi bond present, so the general formula will be CnH2n. There is a double bond, and we term it unsaturated hydrocarbon. Alkynes, CnH2n minus 2. HC triple bond CH. This is the first member of the series. We have a triple bond, and this is still also unsaturated hydrocarbon. So let's go through some of the UPAC name and the common name. C2H4, which is the first member of the alkene series, we call it ethene under UPAC. Common name is ethylene. Next, propene, propylene. First member of your alkyne series, the ethyne. Some people call it acetylene. 2-methyl-propene, isobutylene. 2-methyl-butyl-1,3-diene, isoprene. You encounter these kind of common names in the polymer industry. So again, nomenclature, we have to go through the naming of these compounds. Not because we are over scrupulous or pedantic, but we have to teach you this. Like I mentioned, in the pharmaceutical industry, it's very important to tell people what kind of drugs or chemicals you have inside the capsule that you are going to sell to the consumer. Step 1, name the parent hydrocarbon, single N here, apologies. Find the longest carbon chain containing the double bond, like I mentioned earlier on in the alkane topic. So here we go, 1, 2, 3, 4, 5. So the longest chain contains this functional group here, alkene, so we call it pentene. Not here because, right, if we go through this 6 carbon, then it does not have our functional group. Second, we name the carbon atoms in chain. Okay, so we try both sides and we go for the one with a lower number. Right to left, we have 1, 2, 3, 4, 5, 6. So this is called, okay, 6 carbon alkene, right? This is called hex 2-ene or 2-hexene. The reason is because the double bond occurs between the second and third carbon. If we come from the other side, we will get 1, 2, 3, 4, 5, 6. So it's hex 4-ene. This is not possible. Next, a branch chain. Okay, if they are equivalent, again this is 3-hexene or hex 3-ene. Second carbon, we have a methyl. So we rather have it on the second position than on the 5th position. So next we write it in full. So that will be hex 2-ene. This is 2-methyl hex 3-ene, and that will be called 2-ethyl pen 1-ene. If more than one double bond indicates the positions, use the suffixes diene, triene, and so on. These describe how many double bonds you have present in the molecule. So here this molecule is called 2,5-dimethyl hep 3-ene 7-carbon straight, containing the double bond between the third and the fourth position. 3-propyl hexa 1,4-diene, first and second double bond, fourth and fifth carbon double bond, so diene. Third carbon we have a propyl group. Next, 2-methyl butyl 1,3-diene. All you got to do is just look at the example slowly and try to understand why the name is as such. If you face any problem, you can ask your tutor or myself anytime. Cyclo Alkenes. So the term cyclo means that, right, the carbons are in a ring form close together, and the number of cyclo alkenes, so the double bond is between carbon 1 and carbon 2 for the naming. Look at this. 1-methyl cyclohexene. Why is it so? Remember, 1 and 2 carbon, the first two numbering must be containing the double bond, so it's either 1,2 or 1,2. But since we have a single substituent on the double bond, so we should term this as 1. So this is called 1-methyl cyclohexene. That is called cyclohexa 1,4-diene. 1, 2, 3, 4. Okay, 4, 5, we have an alkene. That is called 1,5-dimethyl cyclopentene, because again 1,2 must be 1,2 or 1,2. But if we go 1,2, then our numbering will be 2 and 3. Remember? Remember? If we go this way, 1, 2, then we will have 2, 3 dimethyl. Right? This is not desirable because you compare the numbers 1 and 2. This guy wins. For alkynes, alright, these are just named like the alkenes, okay, but with the suffix of -ine. So we number the main chain so that the triple bond contains it. And of course the numbering should be as low as possible. We begin numbering at the end nearer to the triple bond. So in this case, 1, 2, 3. Right? 6-methyl oct 3-ine, because this is the main functional group in the molecule. That is called 7-ethyl 3-methyl dec 5-ine. 11-ethyl 2-methyl 6-propyl trideca 3,8-diene. 2 alkyne group in the longest chain. Okay, between the third, fourth carbon, 5, 6, 7, 8, 9. So we have got 3 and 8. 2-methyl, 6-propyl, 11-ethyl. Please note that cycloalkynes are very rare because you want to have a triple bond and then you want to have a ring. What happens? This bond angle is supposed to be what? If you look at it carefully, right, all these bond angles are 180 degrees because they are all sp hybridized, they are linear. But if you want to fold them in cyclic form, then you could bend it. That means you're trying to strain the bond and breaking it. That's why it is not very desirable, and hence they are very rare. For alkenes, right, there are some form of cis-trans and isomerism, stereoisomerism. Recall that in your physical chemistry here, you learn about the orbital overlap sideways p orbital to form your pi bond. And to form sigma bond, it is a head-on overlap here. So we know that for a double bond, rotation is not possible. Okay, it's like you have a pair of chopsticks, or you can using a pair of pans here, right? Double bond. You try to rotate it. What happens is you're going to twist it, right? It's locked, so it's not possible to rotate the bond. Recall in the cycloalkane, these are restricted. We call them cis and trans because they are the same group but on the opposite end. So for di-substituted alkenes, as such, but2-ene. If they are on the same side here, we call it cis but2-ene. Take note the cis should be in italics. The other example will be Trans, butene. Once again, cis-trans refers to two identical atoms or groups. Very important. To have cis-trans or exact, we need to follow some guidelines. In this example here, these two are equivalent. They are the same molecule. They are identical. So they are not cis-trans isomer. The second case, they are not identical. They have two identical reference groups, D, and they're cis-trans. Trans, cis. For the third case, these are not identical. They do not have two identical references. They are stereoisomers. They still are, but they are not cis-trans.